Hey everybody, today what we're going to do is we're jumping into chapter 12, and what chapter 12 is, it's working with non-numeric data. So we're looking at proportions, not means. So let's talk about this a little bit. So 12.1, confidence intervals for one population proportion. So first of all, understand that we're looking at qualitative. Sometimes they call it categorical, but it's non-numeric data. Okay, that's the first big change from what we've been doing. Let's say we're exploring the proportion. Now remember, think F over N. Of the, and let's do this. Let's call that capital N because we'll talk about it as the population. So we're exploring the proportion of the population. With a certain characteristic. All right, so that's the main idea we're looking at here. We're not looking at X bar. That's the big key here, is we're looking at a proportion, not a mean. So for example, say we want to know the percentage of all adults with a college education. Or maybe we want to look at the percentage of all cars that are red. All cars that are, we'll say, painted red. And so anything where we're looking at a proportion, or we can change it to a percentage of something. Okay, so that's the idea. Now, what we're going to look at are population proportion. We're going to call that P. And what P is going to be, it's just going to be, we're going to use the letter X for the values from our population in this case that have the characteristic over capital N, which would be our population size, but where X equals number with the characteristic. And similarly, we can do the same thing for the sample proportion. And the sample proportion, we're going to do something similar to what we did before. We're going to use the P, but we're going to put a little, they call it P hat. And that's just X over N. Again, X is the number with the characteristic, this time in the sample. But again, we call that P hat. Okay, I'll put that in parentheses. So that's the idea. Those are the things that we're looking at. We're going to look in this section, obviously, about the population proportion confidence intervals. So what are the assumptions? Well, here's the assumptions. They're going to look very, very similar to what we've done before. The first assumption, of course, is that it has to be a simple random sample. No big surprise there, I would imagine. Now, number two looks a little bit different than what we've been doing before. We usually talk about it has to be either normally distributed or a large sample. Well, in a large sample, what we're going to consider this time is that X, which is number of successes, or the number in the sample with the characteristic we're looking for, and N minus X, which would be the number of failures. So the number in the sample that didn't have the characteristic, are both at least 5. If they are, we're going to consider the sample large enough that it's going to be normally distributed. And so from there, I'm just going to jump in. We're going to do a problem right away. So let's do this. Let's jump into the exercises. And I already pulled up a problem right here. All right, so I have it as number 4 in here. It says, in a poll, 800 adults in a region were asked about their online versus in-store clothes shopping. One finding was that 44% of respondents never clothes shop online. Find and interpret a 95% confidence interval for the proportion of all adults in the region who never clothes shop online. So just finding the 95% confidence interval. Let's see, so 95% round to 3 decimal places. Well, what we're going to do, we just need some of these numbers. So I'm going to jot down, we have 800 adults. That's N, so N is 800. And they tell us 44% never shop online. Okay, so let's see what we need to do. Now, notice it says click here to view page 1 of the table of areas under the standard normal curve. No, we're going to have StatCrunch help us out. So don't click there. It's going to throw you off. If you click on help me solve this, it's going to lead to how to use the table. We don't want to do that. We want to use StatCrunch. Okay, so let's go in. What we're going to do is we're going to go stat proportion stats. We have one sample. We have the summary because we don't have the data. So we go in, we're doing a confidence interval. So click down here on confidence interval. Notice it already said 95%. We're just going to leave this as standard walled. We want the confidence interval. It says, well, what's the number of successes? Well, they didn't tell us the number of successes, but remember what they said was 44%. So what we have to do is we have to do a little math here. Don't let that scare you. So let's go. Remember, I gave you the formula. I said P hat was X over N. Well, X is the number of successes. X is what's going to go in here. I don't know that. But what they tell me, they told me 44%. Well, that's my 0.44. So that's my P hat. We'll put P hat right over here. So P hat was 0.44. X, I don't know, but they told me N was 800. Well, now here's the math. I just multiply both sides by 800. And you may have known that before. I probably shouldn't put an X there since that looks like that multiplication symbol looks too much like our symbol from before, our actual X. So we'll say times. So 800. But think about 800 times 0.44. We're just saying, well, how many successes did we have? Oh, we had 44% of 800. So even if you didn't do this way, it's the same thing we did where we did the percent times N to find the number. That's all we're doing. So we're just multiplying those two together. We grab my calculator and we just type in 800 times 0.44. It's 352. Now just round that to the nearest. This does come out exactly as 352. So I don't have any rounding here, but we'll just round it to the nearest. But that's what I'm going to put in for my number of successes. So number of successes, 352. Again, that was 44% of the sample size of 800. Number of observations, that was the 800. And that's all we do. Now we run our test. Compute. We've got the data all right in where we can't read anything. And so all I'm going to do is I'm going to put the lower limit. I think they said 3 decimal places. I'm going to go to 4 just in case. So we were 0.4056 to 0.4744. Well, there's my confidence interval. Let's go back and put that in. Pretty sure it said 3 decimal places, which it did. So let's round that off, 0.406 to 0.474. All right, pretty quick, pretty easy. We're just going to interpret that. Remember, here's what that means. Now, the problem, and let's clear this off so we can see, the problem was saying find and interpret a 95% confidence interval for the proportion of all adults in the region who never close shop online. So we're going to say we can be 95% confident that between, and if we change this to a percentage, we could say between 40.6 and 47.4% of the people in this region never close shop online. And so when we look with 95% confidence, that's a good start. The true percentage of all adults in the region who never close shop online is within the bounds of the confidence interval found in the previous step. That's what it is. I don't like that we put this as decimals, and then here they talk about it as a percentage, but I think that should just say proportion. What does this one down here say? With 95% confidence, the sample proportion. Yeah, it's not the sample proportion, it's the whole population proportion. So we will go ahead and check that answer, and we're done with that problem. So pretty quick, not too hard to do that. Now that's back on number 5. I'm going to go back a step to problem 3, and we'll come back to this soon. All right, so let's jump back into the lecture because there's one other thing that they're telling us in this section. So we've done our confidence intervals, but one thing that's happening, sometimes what we want to do is we want to get the confidence interval to be a certain width. So we want the margin of error to be a certain number. Because remember, when we make the confidence interval, what we're doing, the confidence interval is made by, this time, p hat plus or minus some margin of error. If I know what I want that margin of error to be, then it can determine how big of a sample I need to take. So you may see something like a political poll that said 52% of the population are going to vote yes on this proposition, and then they may say with a margin of error of plus or minus 3%. Well, they've already determined the margin of error. That in turn determined their sample size. So if we know the margin of error that we want, so if we know margin of error, again, something that we're wanting to get, we can determine sample size needed. And so this is the other thing in this section that we need to talk about. And the way we do that is this. The formula, which just comes from the formula for margin of error E, is we get N is equal to, now it's P hat times 1 minus P hat, and then times Z of alpha over 2, which we talked about way back in an earlier chapter, divided by the margin of error E squared. And then whatever we get here, we have to round up to next integer. We could just say to next whole number. That would probably make more sense to you. So you don't have to think, oh, what was an integer? Most people remember what a whole number is. Now, one problem with this is we're trying to figure out a sample size, but to get the sample size, we need P hat. Well, P hat is the sample proportion once we've already taken the sample. So we don't have access to P hat. So what we do is this P hat has to be some guess. So P hat sub G is our best guess to what P hat's going to be. And if we don't know, use 0.5 if we don't know. So if you don't have a good guess, oops, not if we know, if we don't know. If you don't have a good guess to what P hat is, just use 0.5. The reason we would use 0.5 is that's going to maximize what that N has to be if we use 0.5. Any value smaller than 0.5 or different than 0.5, we'll say, will make the P hat sub G times 1 minus P hat sub G a smaller number and give us a smaller sample size. The 0.5 gives us the largest one. So anyway, that's our formula. we're going to use that to do this next problem where they ask us to find the sample size. So I'll walk you through one of these. So that's that problem 3 that we had pulled up. Let's look at that. All right, notice here it says n equals, we're looking for sample size. For the specified margin of error, confidence level, and educated guess for the observed value of the sample proportion, obtain a sample size that will ensure a margin of error of at most the one specified, provided, of course, the observed value of the sample proportion is further from 0.5 than the educated guess. So this time my educated guess, and let me write on here, so this educated guess, that is my p hat sub g. Notice it's still 0.5, so even if I didn't have an educated guess, I'd use 0.5 anyway. So this isn't going to change it whether I had the guess or not. Okay, so here's the formula. Let's write that down again and we'll go through it. So the sample size n, p hat sub g, 1 minus p hat sub g, times z of alpha over 2, times e, that quantity squared, and then we're going to round up. Now that p hat sub g on the far left, remember, that's my educated guess. That's the proportion of the population, in this case, the proportion of the sample that I think will have the characteristic. The 1 minus p sub g is the proportion I think do not have the characteristic. That's just using the complementation rule. Okay, so most of this we have. So we can go n equals, well, p sub g was 0.5. 1 minus 0.5, again, you can just put that in as 0.5 if you want to, because when you subtract, that's what you get. E, they tell us, oh, my margin of error is 0.03. That's my margin of error. So I go 0.03. And the only thing I don't have is from this confidence level here, I used that to find z of alpha over 2. And I'll show you how we do that. On StatCrunch, it's really easy. All right, so let's do it. So remember, 99% confidence level. Here's what we do. Let's open this up and let's open up StatCrunch, and I'll show you how to do it. It's real easy from what we did before. All right, so what I do is I go into Stat Calculator's normal calculator. And there's my normal distribution. I'm looking at a 99% confidence level. That means I'd have a 99% confidence interval. So click on between, get this area in between to be 99%. So change this right here just to 0.99. Hit compute, and it's going to say, oh, it's between negative 2.5758 and positive 2.5758. Well, it's this side on the right is the one we want. We don't use the negative. It's not really going to matter because we square it anyway. The negative goes away. But in the table, it's rounded to 2 decimal places. So I will round this to 2 decimal places, and I'll just take the number 2.58. So there, 2.58, we'll put that up here as well. And now I just type that into my calculator. So let's see. So I'm going to go 0.5 times, and then parentheses 1 minus 0.5. And then another parentheses, you may have to hit times, 2.58 divided by 0.03, close parentheses, square that piece, hit equals. I get exactly 1849. Again, if you get a decimal, even if you get 0.1, you have to round up because these always round up. If I had 1849.1, it would mean 1849 is not quite big enough. So to be conservative, I have to round up to the next one, or else I'm not going to have that same confidence level. So I enter the 1849. Let's see what we get for our sample size. Notice that's a really big sample. And so the more confidence that we have that the true population proportion is in there, the bigger our sample size obviously is going to have to be. And similarly, the smaller the margin of error that we allow, then the bigger the sample size is going to be. So anyway, that's the idea there. I'm going to skip from here. We're done with 12.1. We're going to do 12.2 and 12.3 today also, but they're much quicker than this was. Okay, so let's clear all that off. We will jump down. I'm just going to close that. We'll jump out of here. We're coming back here shortly. All right, so let's go back here. We're actually done with this section. So let's jump to 12.2. Now we're looking at a hypothesis test for one population proportion. So there's not a whole lot to say here. Let's talk about, here's the assumptions. So let's see, the assumptions for our hypothesis test. 1, simple random sample. 2, now they write it this way because this is usually the data they give us, is they're going to say both n times p, and notice that's just x, and n times 1 minus p. Well, that's really the same thing as we had before. That's just n minus x. But both of those greater than or equal to 5. So same idea. Oftentimes they're going to give us the proportion here, so they write it as n times p instead of just x, because a lot of times we don't know x. But if we do, we just use x and n minus x just as we did before. But that n times p or x, either way, that's the number of successes. Remember, that's how we found x to plug it in on that previous problem. And then n times 1 minus p, or just n minus x, that's the number of failures, the people that didn't have the characteristic. Okay, from there, that's into my lecture. I'm just going to jump in. We're going to do another problem. So let's go back into the problem set. This time, the problem that I'm going to pick out is problem 8. So let's jump there real quickly. There it is. You can see there's not a lot of problems in this chapter. Hypothesis test. A survey of 1,032, notice that's X. A survey of 1,032 adults. Oops, I said that wrong, didn't I? That was quick. Let's erase that real quick before anybody sees it. A survey of 1,032 adults in a country asking, as you may know, as part of its effort to investigate terrorism, a federal government agency obtained records from larger telephone and internet companies in order to compile telephone call logs and internet communications. Based on what you have heard or read about the program, would you say that you approve or disapprove of this government program? Of those surveyed, 547 said they disapprove. That 547 is X. The 1,032 was N. That was our sample size. At the 10% significance level, that's alpha. Do the data provide sufficient evidence to conclude that a majority, more than 50% of adults in the country disapprove of this government surveillance program? Okay, there's a lot of parts to this. I know right away this do a majority. Well, my null hypothesis, we can start there, is that the population proportion P is equal to 0.50 or 50%. And the alternative, a majority, would be that P is greater than 0.50. And of course, you can just put 0.5 if you want to. You could write 50% if you want to. It doesn't matter. They're both common enough. But actually, the problem says, what's the sample proportion? Well, we know the sample proportion, that's P hat, that's just X over N. So this, we're just going to have to do a little calculating. 547 of the 1,032. So we'll just calculate that real quickly, see what we get. 547 divided by 1032. I get 0.5300, so we'll just call it 0.53. And so notice what they're saying. We want to know if a majority disapprove. Well, in our sample, it was 53%. Well, that's definitely more than 50%, but could that just be sampling error? I don't know. We don't expect p hat to exactly be the population proportion p, but is that too far away that it has to be something other than sampling error? In other words, it probably is that the population mean is above 50%, population proportion rather. So let's go in here, we'll say, oh, the sample proportion was 0.53. Notice it said proportion, so don't type in a percentage there. The sample proportion from this study is the observed, that's what we actually saw, of adults in the sample that disapprove of the government surveillance program. What are the hypotheses for the one proportion z-test? Oh, the null hypothesis test. The null was that p is equal to 0.5, and the alternative was that p is greater than 0.5, because that would mean a majority. What is the z statistic? Okay, now let's test this. Notice these are z and not t. With proportions, it's always going to be a z-test, not a t-test. So let's go in. And that's another thing you have to remember using StatCrunch, because watch how this works out. So let's see, I have the 547 and the 1032 in my calculator, so that'll be good. Because now I'm just jumping into StatCrunch. So let's open up StatCrunch again. Oh, I still have those numbers right there. Okay, so we're going into proportion stats. One sample with summary. Ooh, how many successes? 547. How many observations? 1032. And I'm doing a hypothesis test. P is equal to 0.5. Well, that was handy. Versus P is greater than 0.5. Well, let's get it. Well, there it is. So my z-stat, z is equal to 1.92998. We'll round to there. The p-value is equal to 0.0268. All right. Let's go answer our questions. Let's see. I think we can still see everything there. So my z value to 2 decimal places, 1.93. The p-value is to 3 decimal places, 0.027. All right, let's interpret this. I should have done this before I had all the verbiage there, but we can do this nonetheless. Oh, there we go. There's some blank space for us. Because remember, here's what we do. We say this is less than or equal to whatever the significance level was. The significance level this time was 10%. That's my alpha. And it is less, 2.68% less than 10%. So we say reject the null hypothesis. And then we say yes. The data provides sufficient evidence that proportion of all people that disapprove is, and let's squeeze in here population proportion just to make that clear to all of us, that the population proportion is greater. Oh, well, I'll say is greater than 50%, which of course meant a majority. So that's the idea there. So let's see how they word everything. Reject the null hypothesis. The data do provide sufficient evidence to conclude that a majority of all adults in the country disapprove of the government surveillance program. Now, remember, we're saying it's all adults, not just the sample. We don't have to do a test for the sample. As soon as I found the 53% for the sample proportion, well, I knew a majority of the sample disapproved. I'm doing inferential statistics. I'm trying to use that sample number to infer something about the population. And so, yes, in fact, we do feel that a majority of the population, even in addition to the sample. So we'll check that answer. We're good there. And that's actually the end of that section. We'll jump in. Our next problem we're going to do is problem 10, but that's in the next section. So we'll come back to this in a couple minutes. All right. So back to the lecture. And again, this is a very short lecture for 12.2. 12.3 is going to be pretty much equally as short. Inferences for two population proportions. Okay, so now I'm comparing two populations and seeing if their proportions are the same, just like I did with means in the last chapter. So again, we'll go back. What are the assumptions? Well, the assumptions, simple random samples. And two, independent samples. Let's see. That's not what I wanted. That's what I wanted. Clear all that. Okay. So these have to be independent samples because we've got two populations. Remember, independent samples means the selection from the first population cannot influence the selection from the second population at all. So independent samples. And then thirdly, X1 and minus X1, X2, and N2, oops, I said be N1, and N2 minus X2 all have to be greater than or equal to 5. So what is this? X1, that's the number of yeses that have the characteristic in the first sample. And then the number of no's in the first sample, the number of yeses in the second sample, the number of no's in the second sample. All have to be at least 5. If not, you just need a bigger sample until you can get to that point. Okay, that's the end of my lecture there. We're going to see as we go through the problem what's going on here. So a little bit longer problem here because this one's going to do both a confidence interval and a hypothesis test. All right, so it starts off, and I'm just going to quickly jot down these numbers so that I have them. My X1 is 14, N1 is 60, X2 is 12, N2 is 90, and then I have 0.05 is my significance level. All right, so it says the number of successes and the sample sizes for independent simple random samples, they're just knocking everything out right there, from the two populations are provided for a right-tailed test. Now, again, a right-tailed test, remember what that means, is that the alternative, it's going to be greater than. Use a 90% confidence interval. I'm going to jot that down. Complete parts A through D, and so they give us those values. Now, remember, here's the assumptions. Simple random sample. Yeah, they said it was simple random samples. It has to be independent. Yeah, it says it's independent. All of the numbers have to be at least 5. Well, we have 14. 60 minus 14 is 46. That's greater than or equal to 5. 12 is greater than or equal to 5. 90 minus 12 is greater than or equal to 5. So all the assumptions have been met. We're good to go. All right. Now, p hat sub 1. Well, we have to do a little calculation here. It won't be a big deal. P hat sub 1 is just going to be x sub 1 over n sub 1. So we plug those in. What do we have? 14 over 60. I'll just type that into my calculator. 14 divided by 60, and I get 0.233. All right, let's see. Hey, that one's good. Oh, p hat sub 2. All right, let's do p hat sub 2. So p hat sub 2 is going to be x2 over n2. Well, that doesn't seem so bad. That was 12 out of 90. 12 divided by 90 is 0.133. Well, it looks like there's a pretty big difference in the two proportions, doesn't there? But again, let's do the calculations. Pretty small samples here compared to what we had last time. Is that a big enough difference to show that we actually do have a right-tailed test here, or that we have on the right-tailed test? Now, the pooled sample proportion, we haven't seen this, but I figured I'd show you that here. So when I do pooled, p hat pooled, that just means add up the x ones and add up the n, or add up the x's and add up the n's. So in this case, it's 14 plus 12. It's the proportion in the whole, in both samples combined. So what is that? 26 divided by 150. So my pooled proportion is what they call it, is 0.173. All right. All right, so we're good there. Now it says, okay, check the assumptions. Let's clear all this so we can see what's going on. Check the assumptions. Well, they're all satisfied. We talked about them. Everything was at least 5. They show you these are less than 5. Well, none of those are less than 5. Now, remember, it's not just that N1 isn't less than 5, but N1 minus X1. That would be the number that didn't have the characteristic. So had this said, say, 58 and 60, that would mean 58 have the characteristic, but 60 minus 58, there's only 2 that didn't. Then we would have to say, oh, that assumption's not met. But we're all good here. All right, if appropriate, use the test. Well, so we're doing our test. So let's set up our hypotheses. The null hypothesis is that the 2 proportions are equal. The right-tailed test is going to be that let's see, if it's a right-tailed test, we're thinking that the second one is bigger. So it's actually this way. I think I wrote that, the right-tailed, earlier before. But if P2 we're thinking has a bigger proportion, then that's the bigger one. P1 has a smaller proportion. And notice I'm not putting hats here because we're talking about the population numbers. So let's see. Did I flip that around? Let's go this way. So what they're saying here, and I'll flip that around again. What they're saying is, since it's a right-tailed test, they did want to set that as a greater than, even though with our sample proportions, it was the other way. So let's quickly fix that. So it's our typical right-tailed test where we're going to use the greater than. All right, so let's go ahead and run the test. So let's go in. This is where we need all our numbers, but back into StatCrunch. Stat, back to proportion stats. This time we have 2 sample, again with summary. All right, so number of successes. That's why I wrote all this down. 14 out of 60 and 12 out of 90. Hypothesis test, we're doing a greater than here. Now notice it writes it a little bit differently. So here, remember if those are equal, then P1 minus P2, there's no difference. Their difference has to be 0, or this way with a greater than. So we'll go ahead and compute that. We get a Z value, 1.59, and a P value of 0.0. They were going 3 decimals. If they go 3 decimals again, it's just going to be 5.6, but we'll put 5.65 in case they go 4. All right, let's see what they do. Z to 2 decimal places. And they typically do that to 2 because that's what the table does if you're using the table. The p-value, 3 decimals, 0.057. All right, now before I do that, here's what I want to do. We're going to run the test while I still have a little bit of room here. So remember, here's what happens. We're comparing that less than or equal to give us a value here. Oh, it's right up the top, 0.05, which fits in with a 90% confidence interval. So alpha is 0.05. And notice this time it's not less, that's 5.65%. That's not less than 5%. So we do not reject the null hypothesis this time. And we say no, data is not sufficient. Yeah, they usually word it this way. We'll use their wording. Data does not provide sufficient evidence. And I like it in words, but for time, space, and since they're going to word it anyway, data does not provide sufficient evidence to show that P1 is greater than P2. All right, so now we'll check our answer from before. Let's see, there's our p-value. We'll check that. Yeah, that was right. We'll go down. So at the 5% significance level, do not reject the null hypothesis. The data do not provide sufficient evidence to accept HA. Oh, I hate the wording. You never talk about accepting the alternative hypothesis. I guess you do. The reader has to know, what does accept HA mean? So I would prefer that to say something like P1 is greater than P2, or the first population has a higher proportion than the second population. But we will go with this with the do not provide. So do not reject the null hypothesis. The data do not provide sufficient evidence. And then we go in lastly to run the confidence interval. Well, the confidence interval, again, it's going to be very similar. Let's get rid of all these drawings. We'll go back into StatCrunch, and it's already up, so we'll just pull it up here. And let's say stat. Ooh, maybe we can go into options. Let's see. I don't know if any of those are going to help. We'll go stat, proportion stats to sample with summary, but this time we're doing the confidence interval. And it was a 90% confidence interval, wasn't it? Let's see. Number of successes, 14 out of 60, and 12 out of 90. Let's see what we get. Negative 0.0074 to 2074. And notice zeros in that interval, which is why we couldn't reject the null hypothesis, because 0 might be the true difference. 3 decimal places. Oftentimes they'll go to 3 decimal places with proportions, because that 0.007 would be 0.7%. So it's 0.1%. So negative 0.007 to 0.207. Oops, guess I didn't get there, did I? 0.207. And so there we have it. Examples of each of these. StatCrunch makes the number crunching really quick. If we didn't have StatCrunch, we'd have to do a lot more stuff by hand. We'd have to use the tables. And in fact, it's a lot harder to find p-values. With z's, it's okay. Had we been doing it with a t, like we were doing before when we were testing the means and we didn't know the population standard deviation, we have a hard time finding the p-values. But StatCrunch finds these all for us. I highly recommend using StatCrunch to do this. It'll make your life much, much easier. All right. With that, we're done with this chapter, just those 3 sections. So a lot of stuff. I know this was kind of a long lecture, but hopefully you got in it in 1 or 2 or 3 sittings. All right. Work on this and we'll talk more later.